All right, today we're cracking the code on one of the biggest ideas in AI. How does a machine actually learn? We're going to break down the core concepts behind neural networks, taking you from super simple rules to some seriously complex understanding. So think about this for a second. A computer can master chess, a game with more possible moves than there are atoms in the known universe. It's mind-bogglingly complex. And yet, for the longest time, something a toddler can do, tell a cat from a dog, was a massive, massive challenge. This paradox right here gets to the very heart of why neural networks are so important. See, the reason for that struggle is that older, simpler models, well, they expect the world to follow simple, straight-line rules. They have this built-in assumption that if you increase one thing, another thing will always go up or always go down. More is always better, or more is always worse. And this is where that kind of thinking just completely falls apart. I mean, sure, for some things it works. If you're predicting if someone will repay a loan, a higher income is generally a good sign. But the real world is so much messier than that. Take your body temperature. A nice 98.6 degrees is great, but if that temperature goes up or down, that's a red flag. There's a just right zone, not a simple more is better rule. Now let's bring that back to our cat and dog problem. A simple linear model would have to believe that changing one single pixel, making it a little brighter for instance, should always make the image more dog-like or less dog-like. That's just nuts, right? We know the meaning of a pixel depends entirely on all the other pixels around it. The world is complex, it's nonlinear, and we need a tool that can actually handle that. So the natural next question is, all right, if one layer of simple analysis just isn't cutting it, what if we stack them? What if we just pile a bunch of them on top of each other? Maybe, just maybe, by combining a lot of simple rules, we can create something, well, something smarter. And that's exactly the idea behind what's called a multi-layer perceptron, or an MLP. You've got your inputs on one side, say all the pixels in an image. They feed into what's called a hidden layer, which does some thinking in the middle. And that hidden layer then spits out the final answer. It seems totally logical, doesn't it? More layers should equal more brain power. Ah, but here's the catch. And it all boils down to a fundamental piece of math. Those simple straight-line operations that each layer does, there's a technical name for them: affine functions. And the math says that if you stack one on top of another, you just get another single affine function. You haven't actually created anything new. And this is the bombshell, really. Just stacking a bunch of these simple linear layers gives you absolutely zero extra power. You could have a network 1,000 layers deep, but it would be no smarter than a network with just a single layer. It's like you've just connected a bunch of straight pipes end to end. The water still just flows in a straight line. You haven't actually gained the ability to handle any curves or complexity. So how do we fix this? How do we give our network some real power? We need a secret sauce. And that secret sauce is something called a nonlinear activation function. This is the magic ingredient. After each layer does its simple math, we run the result through this special function. This is the key that breaks the chains of linearity and lets the network learn truly complex things. Probably the easiest way to wrap your head around this is to picture the activation function as a little gatekeeper. It sits on the output of every neuron, and based on the signal it gets, it makes a decision. Does this neuron get to fire and send its message on, or does it stay quiet? It introduces a choice, a bend in the pipe, that crucial nonlinear step. Now, there are a bunch of these gatekeepers. For a long time, one called sigmoid was really popular. It's nice because it squeezes any number into a clean little range between 0 and 1. But it had a huge problem. Sometimes, the signals that the network needed to learn would shrink down to almost nothing, a problem we call vanishing gradients. Then along came ReLU. Its rule is dead simple. If a number is positive, let it pass. If it's negative, just block it, make it 0. And this incredible simplicity turned out to be wildly efficient and solved a ton of the problems that older networks had. Okay, so we've done it. We've added our secret sauce, our activation functions, and now our network is incredibly powerful. But you know what they say, with great power comes a great new problem. What happens when our network starts to learn too well? This brings us to one of the biggest traps in all of machine learning: overfitting. This is when your model becomes a flawless mimic. It memorizes the training data perfectly, every little quirk, every bit of noise. But the moment you show it something new, something it's never seen before, it completely falls apart. It's that student who aces the practice test because they memorize the answers, but they never actually learned the concepts. So to stop this from happening, we actually have to make learning a little bit harder for our network. We need to force it to learn the real patterns, not just memorize the noise. And one of the most brilliant and effective ways to do this is a technique called dropout. And the way dropout works is, well, it's kind of weird, but totally brilliant. While the network is training, at every single step, you just randomly turn off some of the neurons. Poof! Gone for that round. What this does is it forces the network to learn multiple ways to find the right answer, because it can never count on any one neuron being there to help. It can't get lazy and rely on one superstar neuron to do all the work. It's like forcing a basketball team to practice without its star player. It makes the whole team stronger and more resilient. Okay, enough theory. Let's see how all these pieces fit together on a real-world problem. We're going to look at a classic Kaggle competition, predicting house prices. This is where the rubber really meets the road. So the original dataset has about 80 different features for each house. But once you process all that data, turning categories like roof type into numbers a computer can actually understand, you end up with 331 distinct features. 331! Now just imagine trying to find a simple, straight-line relationship between all of those things to predict a price. It's basically impossible. This is the perfect job for a deep network. And here is where we see the whole recipe come together. We use that multi-layer perceptron to give the model the depth it needs. We use those powerful ReLU activation functions to let it find the messy, non-linear patterns between all 331 features. And then we use dropout to act as a guardrail to make sure it's actually learning and not just memorizing. Every single piece we've talked about plays a crucial role. So I'll leave you with this final thought to chew on. This line between genuine learning and just being a perfect mimic is one of the deepest questions we face in AI. As we build these incredibly powerful models, we always have to ask ourselves, are we creating real intelligence, or are we just building a flawless parrot? The answer to that question really is the future of this entire field.